Hi everybody, we're going to look into question 8 and this is going to be on simple and giant covalent bonding. 13 marks over here, so if you think that foundation topics are not tested, you are so wrong. Okay, so let's look into the first question. First question is essentially a definition question. If you've done enough past paper, you have seen this so many times. They want you to describe the forces of attraction in a covalent bond. So what are we trying to describe here is essentially this drawing that we are doing at the bottom. Okay, so this is covalent bond. It is the strong electrostatic forces of attraction between two keywords that's upcoming is shared pairs of electron and positive nuclei. Now things to take note here is the nuclei here must be in plural. And why is that so? It's because, like say for example, I'm just going to use my hydrochloride drawing at the bottom. Nuclei is the plural form of nucleus, right, which most students are more familiar with. And where's the nucleus? Nucleus is the core of an atom. So the nucleus is right over here and the nucleus is right over here. But because when we are talking about covalent bonding, it's going to be more than one atom, so it's going to be nuclei, okay, because there's going to be more than one nucleus, so we have to use nuclei here. Again, if you use the singular form, you will not get the 1 mark here. Okay, another thing to take note here, small things but they do add up your marks, is you can't just say shared between electrons. It must be shared pairs of electrons, because the electrons that is being shared will always be in pairs. Okay, I'm just going to use another color, in pairs. So if I could just quickly give you another example, would be, say for example, nitrogen. Okay, so between two nitrogen, what's going to happen is you actually will have 3 pairs of just no space. Okay, just going to be one more X. Okay, 3 pairs of electrons. Okay, if it's oxygen, okay, then it's going to be 4 pairs of electrons. If you don't believe, feel free to use your periodic table and work backwards towards this. Okay, so the number of electrons will always be in pairs, so this is another set of keywords that you want to look out for. Okay, next, we want to draw a dot and cross diagram of hydrogen chloride. Now, in order for you to draw, one thing you could do for yourself is to use the periodic table and ask yourself how many electrons are there in each of them. So hydrogen is very straightforward, it's only 1, so therefore you see the X is being shared in the middle. For chlorine, there are a total of 17 electrons, 2, 8, 7, but only the valence electrons are used for sharing. So since it only requires 1 more electron to be stable, it will put that 1 electron in the sharing zone and the remaining 6 will be on the outside. Okay, so that's how we get our 2 marks over here. 1 mark for whatever's in the highlighted yellow sharing zone. The other 1 mark goes into the 6 electron that is on the valence part of the shell, not sharing. Okay, next, we're looking at a small molecule. So this is simple covalent molecule. So why is it that simple covalent boiling point, melting point is so low? Okay, so these are the keywords here. You need to first identify what is HCl. Okay, so HCl is a simple covalent molecule. What else are there that is considered a simple covalent molecule? It'll be things like water, it'll be things like ammonia or methane in this case. This is methane, by the way, and ammonia, AMMONIA. So think of the spelling. It's not the same as the polyatomic ion ammonium. Okay, so all these are simple covalent molecules. So you need to identify them. Then you move on to, again, see the common word here is explain. So you need to talk about the why. Okay, so what if they are simple covalent molecule? Why is it that their boiling melting point is so low? It's because with this, their intermolecular forces of attraction is weak. Okay, and therefore little energy is required to boil or melt based on the question. Okay, so one thing to take note here is the correct word to use is little energy. You should not be using less because you are not comparing with another substance. Anytime you are using, they are really strict on this, so please take note of that. Okay, you are not comparing. You cannot use more, be that. So you use little or no or high energy if you are doing the opposite for ionic bonding. So take note of this. Okay. This one is really interesting. It came out, stunned a lot of students. I remember I've got one student who texted me immediately after this paper, and he said like, oh, this one question, this 1 mark question caught me off guard. So this question here is on silicon dioxide. You would have seen this under giant covalent bonding. I know the giant covalent that most of them remember are the diamonds because it's the girl's best friend. Okay, silicon fits into this category of giant covalent structures. So this 1 mark question is asking you, give a reason why particle A represents oxygen atom. Now silicon dioxide, as the formula look like, is SiO2. So how do you justify that A is oxygen and not silicon? Okay, so go to the periodic table. I've done it beforehand, okay, and I've extracted out the information of oxygen and silicon. And if you look at the number at the bottom, this is our mass number, and mass number basically determines the size of an atom. So just based on the mass number alone, you could simply say that the atom of oxygen is smaller than Si. Okay. Another way, things are disappearing again. Sorry about this. It shows that I'm doing live recording, isn't it? I think it's like not so fluff. I don't do editing. There is no time for editing on my side. Okay. So yeah, another thing you can do for yourself is, so this again, I'm going to write mass number. Okay, you could use the number of electrons, okay, to help you here. So if there's oxygen is 8 electrons, so the electrons will be arranged in the configuration of 2, 6. For silicon, it will be 2, 8, 4. And you could see that that alone would represent the different numbers of shells, isn't it? So you could say that, I'm going to write this in. Oxygen has 2 shells and silicon has 3 shells, okay? So if the number of shells is more, then the atom's atomic size would be bigger as well, okay? Another possible answer is silicon is connected to 4 oxygen, while oxygen is connected to 2 silicon atom. And how, again, you'll be asking how do you know this? Okay, it's because of the group number that they are found in. Now oxygen is found in group 6, so basically means it will want to bond with 2, so it will form 2 covalent bond, whereas silicon, like carbon, is in group 4, so it's able to connect or form 4 covalent bonds. So that's how the third possible answer can come in. Okay, so it's 1 mark, but it challenged your understanding, it challenged on whether you can use resources like your periodic table. It's always printed but hardly used to help you support and construct your answers in an exam setting, especially for a question that have never come up before. Okay, this is also another part of the question. So linked to that, okay, you have got silicon dioxide and calcium oxide. And so this question is also questioned by a lot of students, like why silicon can react with calcium oxide. So if you remember, there's this one part of your syllabus that talks about types of oxides, okay? So if it's a metal oxide, they are basic oxides. So things like, so our calcium oxide is a metallic oxide, okay? And the opposite would be non-metal oxide, and non-metal oxides actually form acidic oxides, okay? So when you have bases reacting with something acidic in nature, usually neutralization can take place, okay? So understanding that silicon dioxide is an acidic oxide because silicon here is a non-metal, okay? So it's an acidic oxide, it can react with basic oxide, and the process is known as neutralization. So this is 1 mark question. Now for those of you who have read up more than that, you might have come across this thing, what we call blast furnace. It has been removed from the syllabus, thankfully, for most of you who don't like to memorize things. Blast furnace is how we extract pure iron out from iron ore. This is actually the last final step of blast furnace. The silicon dioxide is actually the impurity that comes in as sand, and we use calcium oxide, which is basic in nature, to react with it. And what we get here is, I would say a conventional name of it is slag. Okay, so that's the outcome, and this is the fifth and final equation of a blast furnace. So it's very interesting. They are using like things that they have removed from the syllabus, but it can still test you based on the property and concept that you still need to know based on the syllabus. Okay, right, last 5 marks here, focusing on nothing but silicon dioxide. Okay, so silicon dioxide, they say, has the same structure as diamond, so you need to link it. So this is a clue for you to link it, okay, to diamond. And what do they want you to discuss? They want you to first discuss structure, and then you discuss bonding to help you to support and understand why silicon dioxide is very hard, which is same as diamond, isn't it? And has very high melting and boiling point. So when you are structuring your answers, you will want to look into focusing on structure. If it's 5 marks, then you can allocate half of it to structure and the other half to bonding. So this is to make sure you get full 5 marks here. So let's see how, let's just focus on bonding first. Okay, we're going to focus on the bonding in silicon dioxide and how that can help you support the reasoning of why silicon dioxide has very high melting and boiling point. So looking at silicon dioxide, the structure here, what kind of bonding is it? You can see that the lines are here, and they are both made out of two non-metallic elements. So we've got silicon and oxygen, so this is definitely covalent. But this is a structure, not a simple molecule. So when it comes to bonding, what you want to discuss here is that okay, so what we have here is many strong covalent bonds inside this giant covalent structure. So what I like to do here is to first identify what kind of structure is silicon dioxide. So I go straight to identifying that it's a giant covalent structure, and in this structure there are many strong covalent bonds. And what are these strong covalent bonds is, again, by going back to this structure, every line that you see here is covalent bond, okay, and there are many of them, therefore it results in a very strong covalent bond in the entire structure. Okay, whatever is green here is really for you to understand. Okay, so because after you understand, then it makes sense why the answer would look like this. Okay, so what if there's a lot of strong covalent bond? Then in order for you to actually melt silicon dioxide, is you need to break every single of this yellow line here in order to melt it. Okay, you cannot break like just 10 and you expect the silicon dioxide to be in liquid state. You need to melt every single one of them. So what does it mean then? It means that a large amount of energy is required to break the strong covalent bond. Okay, and this is linked to the high melting point. Okay, so just by writing whatever I've mentioned so far that's highlighted in yellow will have gotten you 3 out of 5 marks. Okay, then we look into the structure part. So what kind of structure is this? If you are stuck, then look around. What are the information given in the question? The information here is diamond. So again, if you cannot recall what silicon dioxide structure is, I'm sure you can recall what diamond looks like, right? So diamond have a tetrahedral structure. The word tetrahedral means it is connected to 4 other things. So what in this case is connected to 4 other things is the silicon atom. So if you're not sure, again, the diagram is supposed to help you here, right? Since we have already established that A is our oxygen, that means the black and bigger atom here will be our silicon, isn't it? Okay, so our silicon here, I think the one right in the middle is easier for you to see. So it is connected to 4 other oxygen atoms. And using that will help you structure your next mark here. Okay, so tetrahedral, because every silicon makes 4 bonds or bonded to 4 other oxygen atoms. So just writing these 2 alone will have gotten you your 4th and 5th mark. That basically means you have a full mark here already. But if you want to secure and make sure you have every single thing covered, then you move on to number 6, right? So the atoms, they are unable to slide over each other because there's nothing that's moving in this tetrahedral structure, right? There's no layers, not like graphite, okay? And so because the atoms cannot slide over each other, this results in a really hard structure. And that goes back to you being able to, that you being able to answer the property of hard and high melting point. I'm not sure who's calling me, okay, but I should pick it up. Okay, so one final thing to mention here is if you mention anything along intermolecular forces here, intermolecular forces, okay, you will not get marks, or you will not get a full marks, or ionic bonding. Now, intermolecular forces is only for simple covalent molecule, and that basically means it's for our like water, carbon dioxide, HCl, etc. Okay, so with that, I'm going to pause here, and hopefully this question has been helpful to help you differentiate the keywords between simple and giant covalent bonding. Again, if you have found this useful, like, subscribe, or drop me a DM. See you on the other side.